kick us off. So hello, everyone. I wanted to say welcome to this second webinar in the 2021 Earth Science Information Partners Innovation Webinar Series, which follows ESIP's 2021 year theme of leading innovation in Earth Science data frontiers. My name is Megan Carter, and I'm ESIP's Community Director. This webinar series, which is sponsored by our partner SAIC, explores examples of innovation, stories of developments that didn't seem innovative at the time, but were innovative in retrospect, and examples of what innovations are needed in the future from a wide variety of perspectives. Today, we're delighted to feature the European Space Agency's B-Lab and the InCubed program that sits within it, which focuses on developing innovative and commercially viable products and services that leverage the value of Earth observation imagery and data sets. Over the next 90 minutes, you'll hear about the Lab and about the InCubed program, as well as about 4 activities at various stages of development that have been supported by InCubed. There will be a Q&A component towards the end of the webinar, so if you have any questions throughout it, please pop them into the chat box here in Zoom, and we will address them as time allows. I would like to remind everyone that this session is being recorded and that it will be posted to the ESIP YouTube channel after it's over. So if you're not familiar with ESIP, we wanted to give you a warm welcome. We're glad that you joined us for this webinar. ESIP strives to be a leader in promoting the collection, stewardship, use, and reuse of Earth science data, information, and knowledge that is responsive to societal needs. For more than 20 years now, ESIP has helped members of the Earth science data community to find each other across traditional boundaries, to leverage each other's expertise, and work together on common data challenges and opportunities. ESIP is funded by NASA, NOAA, and the US Geological Survey, and we have about 170 different partner organizations that span the federal, private, and academic sectors. To help our science data professionals work together, ESIP fosters rich collaborative experiences, including numerous community-driven virtual collaborations, the ESIP Lab, which supports the development of innovative applied earth science technologies, and through 2 annual conferences. And you can see that our next meeting will be in July. It'll be fully virtual. Registration is now open, and we'll share the full agenda soon. We'll feature upwards of 50 community contributed breakout sessions. We have a great lineup of plenary speakers and numerous networking opportunities. I encourage you to check it out and to join us if you can. So without any further delay, I'm excited now to welcome Amanda Regan, InCubed Program Manager and Head of the Fee Invest Office in the Earth Observation Future Systems Department at the European Space Agency. After her presentation, Amanda will then introduce the 4 subsequent speakers who will showcase specific examples of developments that have been supported by InCubed. So take it away, Amanda.
Great, thank you, Megan. So let me share my screen. Okay, Megan, if you can just tell me if you can see my screen.
I can see it. It is moving slowly, but it's there.
Okay, one thing that I will do is just stop my video. That'll increase my bandwidth slightly. And okay,
looks good. All
right. So do you see it? Okay.
Yes.
All right. So good morning, and to any Europeans, good afternoon. I'd like to give you a quick overview of the Lab and also the Investing in Industrial Innovation program, which I'm managing at this precise moment. Let me just get to the next one. So we are standing in the middle of a perfect storm in the Earth observation sector right now, with a lot of new stuff that is just crashing into our industry. So we have more Earth observation data than ever before. We have Copernicus, which is built on Landsat, another data stream heritage, providing long-term systematic data that businesses are starting to build credible business cases on. We have major technological advances. The performance per cubic meter of satellites is just exploding. We have cloud computing and huge computational power that we really didn't have 10 years ago. This is bringing in also an ICT component. So as I said, the cloud computing and the computer power, but also a connected thinking, which we didn't have before. So there is more of an edge computing, distributed systems rather than centralized systems. And really, all of this is bringing in a new entrepreneurial spirit into the sector, which is bringing in new investment, new money, new players, and new thinking. And so this is the reason why the FELAB was actually created at the European Space Agency. So the FELAB really, it aims to accelerate the future of Earth observation through transformational innovation, really trying to lead to competitiveness. So we have a pathway through the FELAB, which starts at blue sky ideas. So we have very much more research focused on the left-hand side, looking at nurturing and developing good ideas, and then moving towards the right-hand side, looking at entrepreneurial initiatives, and then making Earth observation products and services market ready. And we look at this through developing business cases, through also developing different kinds of prototypes and use cases. So in the FELAB, we have two offices. We have Explore, which really focuses on connecting the sensor revolution with the digital revolution. So they focus on artificial intelligence, for example, digital twin, this kind of, and also distributed systems and architectures. And then on the other side is the office that I'm looking after, which really looks at trying to stimulate and develop the commercial Earth observation sector. And this is through a vehicle known as InCubed, which is investing in industrial innovation, so InCubed. And this is a new program which was kicked off at the end of 2017. So if we go back to the FELAB pathway, you can see that the Explore office really focuses more on the left-hand side of the pathway. And then there's a kind of a handover to the Invest office, where we're looking at more the commercial side of things. Now, because Explore is much more research focused, we're not saying that every piece of research will have a commercial outcome, but we like this mindset to be there, so that in case there is something that is commercially viable, this can be handed over to Invest. But Explore very much interact with many other avenues within ESA as well. So these are the kind of things that we're working on. So this is the Explore office, looking at blockchain, quantum computing, AI in particular, and digital twin. We're looking at building use cases and also prototyping really fast concepts. So this is more on the research side, and we have a number of research staff inside the lab. If you want to work with us, by the way, we have a number of different fellowships. So people from companies, from academia can come and spend from a couple of days, a couple of weeks, a couple of months, and even we've got a couple of people that have come for a couple of years to spend time in the lab and be able to work with European data and also the facilities that we have. We have opportunities for professorships and research fellowships as well as trainees. And if you want some more information, as of about 2 weeks ago, we have a new website, which you can see here. So the InCubed program, which is what I'm managing, this is a co-funded program, which means that different member states, different countries, they subscribe to the program. And also industry and companies, they also co-fund their activities. We have subscriptions from 18 member states with a total of just under 100 million euros. And in fact, it's just been topped up a little bit by one member state, so it's now above 100 million euros. And we're really looking to stimulate and develop the commercial sector, looking at products and services in the EO commercial sector, and we look for three main things. First of all, commercial viability. So we're not a technology development program. We're looking for the companies to generate revenue by the end of the InCubed activity. We're looking for them to innovate and do something new, and I'll talk about that in a second. And also, we're looking for commercial customer engagement at proposal stage. So commercial customers can be there in terms of beta testers or validators. There can be letters of interest, letters of support, but there has to be that commercial focus. And we have 4 examples after this presentation: 2 upstream, so 2 satellite developments, and 2 downstream, which we'll explain a little bit more in detail. So InCubed has an end-to-end scope, so it means that we co-fund everything from satellite developments, systems, subsystems, down to web platforms and ground segments. We typically co-fund 50-50, but we can support up to 80% for small and medium-sized enterprises, and it depends on the country that the company is coming from. We have in our present portfolio just under 60 activities, and they range from around 150 kilo euros, and that's total cost, to 17 million, which is our biggest satellite development. So what we offer in InCubed is zero equity co-funding. We also take each submission and really analyse how best ESA can support the activity, so you get real personalised guidance. We also give companies access to the facilities that we have in the FELAB and across ESA, and we're starting to connect with private investors and venture builders to actually strengthen the InCubed pipeline. And we're creating a community to be able to build an ecosystem around this approach. These are the present participating member states that have contributed to InCubed, but I also want to say that we're open to partnerships from non-subscribed countries on a self-funding basis, and we're at the moment exploring this with countries that want to do commercial developments with us. This just gives you a quick overview of the pipeline. So we start with an idea pitch where the companies give a 15-minute pitch to see if it's a good fit for InCubed, and we do this with the company delegation as well. And it just gives a better understanding of what the company has in mind. And typically what we try and do from idea pitch to contract signature is in the order of a few months. We're always trying to streamline this to get this through as quickly as possible. If you're interested, we also have a website as well, and you can find all the information about the program there. Because we're talking about innovation today, I thought it might be interesting to give you a flavour of the kind of innovation that we do see in InCubed. So, for example, we have disruptive innovation. So, for InCubed, this is something that's completely new. So, examples of this are an app store in space. This doesn't exist yet, so this is disruptive innovation. Another example is optical communication based on distributed architectures using ledgers, so a blockchain type of approach. We also have, for example, what we call incremental innovation. So this is when there's something that's existing already, but the idea is to add a delta to an existing product or service. So one example is you have an optical product already, and then they want to actually add a higher spatial resolution. This is incremental innovation. Another one, I've called it disruptive incremental innovation. So this is something that, for example, the product, it already exists, say, for example, an optical data product, and the company are wanting to add an interferometric data product on top. And this creates new synergies and new insights. Another example could be mission planning as a service. So the function already exists, but the service model or the business model is new. And the last one is incremental disruptive innovation at national level. So for example, the product might exist already in a different country or in a different place, but particular countries want to develop their own national capabilities. And we've seen this both upstream and downstream. So this is not an exhaustive list, but it gives you a flavor of the kind of different types of innovation that we see in InCubed. Okay, that's everything. I would like now to hand over to Marco from cosine, who's going to give an overview of his experience of InCubed and Hyperscout 2. So Marco.
Thank you, Amanda. So I'll share my screen. Hello to everyone, first of all. So let me know whether the sharing works fine for you.
Looks great.
Very good. So yeah, thanks first of all to everyone to invite me to give this talk. It's an honor to represent a little bit the first, I think, one of the first incubers. And so I'm from Cosine Remote Sensing, a Dutch company. I'm the managing director, one of the managing directors. And I'm gonna tell you a little bit about, first about the company, very quick, so that you get also a bit of flavor who we are, why we're doing this, and then about the specific activity that we did with InCubed and Philab in general. So Cosine is a company, a Dutch company that exists since 1998. So now it's definitely not a startup. So it's almost 25 years old company. We're about 55 by now. And we half of us, it's actually with a PhD level education. So give you a bit let's say the kind of research we do inside. We are organized in 3 main units. The one on the left, high energy optics, deals with indeed optics development for the high energy regime. So it means X-ray, extreme ultraviolet, this kind of wavelength. And we are busy indeed also with this on the largest Esa mission, that is the Athena, looking at the black holes and energetic universe. On the right is the remote sensing part, that is the one that I manage. And here we deal with all optical instrumentation, usually small and compact, for small satellites, but also for planetary research and planetary science, and but also for when now we are looking at airplanes, UAVs, and also other kind of targets. And in the center, you see our gate to the terrestrial market. What we do, we develop a lot in space. As you probably know, in space, usually the margins are limited to what you can do in R&D. And then in the, let's say, terrestrial market, we try to leverage a bit with more profit, more revenue in like the medical, oil and gas, and for the pharma kind of markets. So in the remote sensing part, we are working on different technology lines that we have in the company since the start. Our company starts looking at really an application like planetary science, where everything needs to be small and capable. So from there, we build up quite a lot of building blocks in the company. Now we try to exploit for the Earth observation market, because there is a very good match, especially with indeed the new space and small sats. So what you see is a hyperspectral, spectropolarimetry, LiDAR, spectroscopy, infrared sensing, and then since a few years, artificial intelligence is taking really a lot of our effort. Integrated photonics for calibration devices, and software. It's all over the place, of course. So hyperspectral is a little bit the core of this presentation, and especially because the products that we have been developing, and then thanks to InCubed also to consolidate and finalize and also launch on the market with a let's say a more powerful how to say a footprint. So actually the Hyperscout is a very compact hyperspectral system. Has been deployed in space in 2018 in the first quarter. We are talking about 1 unit in terms of CubeSats, or a little bit more, 1.5 units, and also let's say less than 2 kilos, with 45 spectral bands, very large field of view. So this was intentionally made quite large, and also sacrificing a bit the spatial resolution, because our target was the spectral resolution and the temporal resolution. So we would offer on the market something a bit orthogonal to what is there, because everyone is going for looking at smaller pixels. So we wanted instead to look at very narrow spectral bands and all over the world as often as possible. So this has been already, let's say, worked out together with the Philab. We did the first project where we looked how to to cross-calibrate to enhance the quality of the data from the first hyperscout. So you can imagine, being the payload very small, there is no really room for calibration devices on board. So the absolute radiometric accuracy, the spectral calibration, these are things you have to work out with vicarious calibration. But we looked here together with indeed the PhilLab how to exploit artificial intelligence by cross-calibrating. In this case, hyperscout with the Sentinel-2, but a bit more generalizing the concept with, let's say, small subs with institutional satellites. And you can see here, of course, we did quite, let's say, a number of acquisitions with the first hyperscout. Here you see a few snapshots here and there, and also one of the first results that was to really do the processing as far as possible on board. So what you see here was the first data cube generated in orbit. This was also again back in 19, I think, the first time they really will build up a data cube in orbit. And now with the PhilLab, the InCubed, we went a bit over to see how far we could go with the final product, data product. So with Match, we looked indeed how to get an hyperscout. Typical hyperscout scene is this one. So this is the SWOT that you can see. So usually is if you use the full field of view, is about 300 kilometers, actually 330 the hyperscout 2, but usually we download a sub part or let's say region of interest. And what you see here is how an hyperspectral scene looks like. So of this small region of interest, here you see all the bands. Of course, here is not reported the wavelength, but you can imagine that each wavelength is a different spectral response from the target. And you can see, interestingly, that all the fields, these are agricultural fields. Actually, you can see how the response change wavelength by wavelength. These already tell you how much information is in there that actually you can use for extrapolate, many more information, actionable informations. So with Match, we looked at, if you see the same scene with the Sentinel, you see an histogram of the response. You can see how different between hyperscout and Sentinel. We elaborated many different neural networks as a trials and to test. And let's say in the end, what we got is a very nice result. So in terms of similarity between the histograms, we got very close to 1. So it means with no calibration effort, let's say before launching the payload and operating in orbit, you can achieve an accuracy of your calibration accuracy that is close to the one of Sentinel. So it means for us going below 3%. So it's very high with a small sat. This is can enable very interesting data product. So you can see the results on NDVI maps. You see one from Sentinel and one from hyperscout. This is again the histogram difference between the two. So you see that it's very close to 0 with a very narrow standard deviation. So then the interesting part comes with the second generation, hyperscout 2. It's been launched last September, so in the third quarter 2020. And indeed, with the PhilLab and with the InCubed, we were able to enhance this product by adding also a thermal channel, thermal infrared, so really to measure the temperature of targets. And also we added an artificial intelligence accelerator in hardware, so a BPU, vision processing unit. And so this was called Fisa as experiment that was running on board the hyperscout. So we really did a lot of really innovation in very short time. So the overall development was less than a year by adding in the same envelope let's say all the relay optics and plus the focal plane for a thermal sensor. That per se is a very complicated matter if you want to really do it in a proper way. And plus all these AI boards and chips, plus all we were able to develop also the full processing chain from the raw data up to the first application data product. In this case was cloud screening, so we really tried to implement the cloud screening in line, means be able to detect pixels that are affected by clouds, and therefore in the future finding a way to eliminate these from the downlink, and therefore making downlink capacity, let's say, much more affordable to us. So this was in the context of the FSS-CAT mission. It was also a mission granted by ESA to a consortium of companies, university, for which the use case was polar snow monitoring and plus soil moisture. Hyperscout was added on top of the mission to enhance the products of this mission. So really to get better resolution when you come up with the soil moisture of the products and also this ice information as well. So what you see here, some snapshot of the data we collected. So operation went over from September to last February actually. Now we are in a pause and we are negotiating to continue working for ESA for acquiring and making available all this data to Copernicus as a third-party mission. This is something ongoing as a discussion and could start very soon in case discussion, let's say, turns to be positive. What you see here is a typical, you see the full SWOT here. So this is like Lake Tartar. It's a very interesting scene here. You see water and very with a high contrast scene. So you see a lot of terrains with a lot of features that are very well without clouds, of course. This is in Iraq, and also the thermal. This was during a commission, the first thermal stripe that we got at the same time. What you see here is the Baltic Sea, so at the bottom left. And what you see here is a mosaic of different acquisitions and coming indeed from our sensor, mainly the visible and infrared sensor. So I'm trying to speed up a bit. Tell me if in case I'm too fast and you miss some bits. We can also take questions later. Then, as I said, one of the very interesting development we did in this mission was to add the artificial intelligence hardware and software during this mission. So what we have been able to do again in a very short time with another consortium compared to the one of the FSSCAT mission is to put together the full development and processing chain for cloud screening in flight using artificial intelligence, and also for the first time a very low power consumption, low energy consumption VPU, vision processing unit. So what you see here is the typical processing chain. So we have to do in our payload the full acquisition, and usually hyperspectral acquisition is very heavy. So we're talking about 1.2 gigabytes per acquisition. So this means after, let's say, a few orbits, you accumulate and get into terabyte very quickly. So here we have to do a large pre-processing in order to get, to a first spectral data cube. Then we have to prepare this data in order to run our artificial intelligence algorithm on board, and then we do the inference, and therefore we get the results down. What you see here is the first ever AI image generated in space and downlinked to Earth. This was also announced during the FEE week last year, where the former director of Earth observation, Esa Qualifications, also proudly said that this was a very first innovation of this department. So you see more acquisition. The interesting part I want to show is the thermal part. So what you see to the left is the typical acquisition made by Sentinel-3, so one of the large Copernicus satellites. And what you see to the right is our Hyperscale 2 acquisition. Of course, you can see these very similar images. You can already imagine that Sentinel-3 is much more performant, of course, much more accurate, much more stable. On the other hand, you see with the, let's say, you see also the size. You see here the size of the Sentinel-3 SLSTR payload, and while Hyperscale 2 is very tiny. So at the same time, you can understand how much power there is in such a small component, such a small payload, and how far we can actually use the Sentinel, as we did for Sentinel-2, as cross-calibration point for us. So this makes the payload, I think, very powerful, because now we can go from visible near infrared up to thermal infrared. Therefore, closing the full energy budget, you can go into agricultural fields, into energy, and urban islands. We are looking at so many applications, water pollution, and so on, because now we have the full spectrum available to us. And also, being so small, you can actually deploy many in space. As this is, of course, the usual story of nowadays of new space. So you can deploy constellation. This is actually true. So we have already in orbit a number, and with our customers and partners. So we already have a constellation of hyperspectral that can go down to a very interesting number in terms of revisit. You see here also a demonstration for us that we can actually catch also fires, because we are looking now also an application with other partners about bush fires. You see here, this was during the fires in California last year. You see very clearly, let's say, that we found out already with our data, let's say, what kind of burn areas and fire we could find. So we in the pipeline there is for this year, as I said, to go to 5 units in space. So we have 2 already flying, other 3 basically already built and tested, 2 already actually delivered, and we are negotiating a few others. And with all these partners, we're building up kind of indeed a network of MOU between all of us, so that we can use all these payloads and spectral, thermal, artificial intelligence all together. This will mean a very powerful constellation with many spectral bands, so you can achieve, let's say, many applications by using the same space asset. A little bit about InCubed. So what is my experience or our experience in general? So we were able, as I said, to generally to consolidate our space product that was already existing before, only with the veneer. So we added, first of all, a lot on calibration. Then we expanded in terms of spectral bands. We added 3 bands in the thermal infrared range. That is a very difficult channel for let's say, the experts, they know what I mean. Integrated the AI hardware, full processing chain up to cloud screening in orbit, and do quite a lot of experiments. So we have now actually a test lab in space running for us, for Esa, and for any partner that actually wants to do that. I would say that my experience that InCubed is very well suited for parties that want to enter into EO market, or they want to consolidate their position, because they get, apart from funding, of course, that's very important, but also they get the skills of Esa. There are many technical experts that you can use basically for free, because they are reviewing you or they are supporting you, but you also get access to the network. And Earth observation is a very big network. If you enter in this way, you actually get just in the center of mass of this network. So it's very interesting. The challenge from me, I managed this project, was we had to do this in a very short time. So really, we had a lot of pressure for that, also on our side, but Esa also want to achieve a lot in a very short time. So it was very difficult. We really had bad time as well to get through all the obstacles. But in the end, we have a fully functional and very good performing payload in space that will be used in next years as well, because we have experience from the previous hyperscape can stay in space for at least 3 years so far. So next is really to consolidate this coordinated constellation. And now we have 5 by the end of the year, but this is going to grow. And how it grows, the revisit time goes down. Already with 5, 6, we achieve daily revisit. But any partner that adds to it, you can go to sub-daily. So with 12, 13 units, we can go to even hourly revisit worldwide because of the big field of view. And therefore, we will also work on AI on board in a distributed way, so that each satellite can address different AI applications, and then we can do this in a coordinated fashion as well. So all this is under, let's say, consolidation, and I'm sure very soon you will hear more, and hopefully also through the InCubed channel as well. It's not only us, we have large number of partners in the different developments. I'll leave it to you to read it later. But it's very comprised very specialized companies and universities that help us to really get to this kind of results. So that's on my side. I hope that yeah, let's say the message I want to give about our developments, but also how important was InCubed for us is there and reached you as well. Thanks.
That's great. Thank you, Marco, very much. Okay, so that was an example of an InCubed upstream activity that we have in the pipeline. I want to go down the Earth observation value chain now and introduce Charlotte from TechWorks Marine, based in Dublin. Okay.
Just bear with me a second. Hi, everyone. Can someone just confirm when they can see my screen?
Yep, we can see it.
Oh, and I moved my laptop, so my camera's come off again. Just bear with me. The joys of technology. Hi, everyone. So I'm going to bring you back down to Earth with a splash. From space into the ocean. So my name is Charlotte O'Kelly. I'm the managing director of a marine data company called TechWorks Marine, and we're based in Dublin in Ireland. And I'm going to give you some of, I guess, my insights on innovation, marine monitoring, and Earth observation. It's slightly different to Marco's presentation, but that's the interesting part of the mix. So as a brief introduction into TechWorks, like Marco, we're not quite as old as Marco, but we're not far behind. We set up in 2002. And this simple diagram gives you an overview of the sectors we've been operating in. So we really operate within the coast. So if I can see, it's what I call the coast, and I know this is a very kind of research-based audience. For me, the coast is what I can see from the shoreline. So it's where remote sensing generally doesn't work very well, and it's where most of the commercial activity happens, which is our bread and butter. So aquaculture was one of the first areas we worked in. And then marine renewables, notably tidal and wave resource assessment. So we did a considerable amount of that in situ resource assessment on tidal and wave energy sites around Europe. In 2009, we started a relationship with Esa in terms of Earth observation data services. And our first project was looking at jellyfish blooms and forecasting jellyfish blooms using neural networks. That's still a subject of interest. We've been working in the domains of ports and harbors, water, and also national infrastructure monitoring. So that just gives you a bit of a flavor of what I'm going to talk about now. So we are in what I would call the full data value chain. And that's why I specifically have put commercial data, commercial information, and then how we link that with public open data sets. So TechWorks Marine, we come from the world of operational oceanography. So the design and development of real-time in situ monitoring platforms, as you can see here on the left-hand side, these tend to be quite costly and therefore are an issue for a lot of commercial clients or a lot of just normal monitoring that people want to do. We link that in with our data portal called COASTEO, which I will talk to you about in a minute, which is basically our data management and delivery system, which converts our clients' data into information they can use to carry out their operations. And then I guess this is where the Esa link comes in. We use Esa data products from Sentinel-3, Sentinel-2, and Sentinel-1, for example, to provide value-added products and services to our existing and also to our new client base. And so I'm going to basically talk to you about this in the presentation. So just to summarize what I just said previously, TechWorks Marine, we measure from the seabed to the sea surface. We measure high resolution data at very low spatial resolution, but over very long time series, so at 2 Hertz, 4 Hertz, etc. That data comes back to our clients via either cellular or satellite or both. And we have been working so since 2009 at validating and linking this with Earth observation satellite data. This is an image actually in Sweden of a buoy network we have there, and basically live chlorophyll from buoys and comparing it with chlorophyll from the satellite overpass on the same day. I actually think that's a VERS satellite overpass. So in TechWorks Marine, we make two things. We make data acquisition systems for marine data buoy platforms. So basically data loggers that can plug and play different sensors, be it nitrate sensors, current meters, acoustic recorders for marine mammals, and send that information back to you, the user, through the COASTEO portal, which is what I'm describing here. So on this portal, you can manage and monitor your in situ infrastructure, be it deployed on buoys or on other platforms. You can also import data from other monitoring platforms. You can view real-time in situ data as well as visualize Earth observation products, compare different products in space and time, and then download this either ready to insert into a report if you are a user who just needs access to the data to make the decision, or if you're a scientist, you can import it into whatever processing package you're using. Up above that image is one image of our mini buoy system, which is what InCubed has funded. This is the mini buoy system in Dubai, just looking at Dubai Marina. So we were funded through InCubed last year to work on a project called COASTEO. Those of you who are in the marine monitoring sphere will know that putting out long-term data buoys is extremely costly. requires large ships, which are even more costly, and the through-life costs are significant. So our interest was to basically, we developed a small data buoy, a small data buoy that you can see here on the left-hand side, and I'll go into more detail on it in the next couple of slides. This sends us real-time data using Internet of Things to Amazon Web Services, where we can basically interrogate it directly, linking this with satellite data to validate satellite data on the fly, so that we can then provide our users and new user groups with validated Earth observation products. So we're in the middle of this project at the moment. We specifically focused on Ireland, and actually for this presentation, all my images are of Ireland, apart from the one I showed in Dubai and the Swedish one, just because, as Marco alluded, cloud, we have a lot of it. It's a real challenge. If we can make it work here, mostly at the Earth observation side of things, it can work anywhere. By the same token, we have extreme wave climates and extreme weather conditions. So if our in-situ systems work here, they can work anywhere as well. So this is basically a very high-level overview of COASTEO. And it might sound simple, but actually most people just look at satellite data in my world as a pretty image, rather than an image that enables them to make a decision, management decision based on that. So why was this of interest? Well, the buoy platform that you see on the left-hand side, that's Dublin Bay, by the way, on a summer's day, as you can see, nice and cloudy. That buoy platform, fully instrumented, is several $100,000 euros. So that's part of $300,000. The mini buoy platform that you can see here on the right-hand side is much smaller. So therefore you need much smaller boats to deploy. It's for use in coastal environments, and it's not necessarily for the same long-term deployments, but it's to give you quick validation tools. And really it's about short-term monitoring. We developed mini buoy with the Irish Environmental Protection Agency because they wanted a system that they could deploy at short notice to respond to pollution incidents. So the suite of oceanographic sensors on the mini buoy is more or less the same as the one that goes onto that larger buoy, just to put it in context. And I guess the innovation is about reducing size, making it more accessible. Space data, oceanographic data is not accessible to most people, and to users and stakeholders within the coastal zone, it's often extremely difficult to access this data. So models are validated with very small validation data sets, etc. And this is where we were really trying to fill a gap. I'm now going to just give you a few brief examples of some of the cool things we have been doing in Dublin Bay, and how we have been linking commercial and research work together, and how we have been innovating on the fly. Much as Amanda and Marco were talking about, things happen very quickly. And in a way, if you have equipment in the water, you can carry out innovations and piggyback on existing systems, because as I said, putting out oceanographic buoys, much like putting up satellites in space, is just a very costly business that needs lots of planning and structuring. So my company has had a contract with the Dublin port. That's Dublin, by the way, that satellite data there. And we have had a contract for the last 4 years, which is about to get extended, to monitor water quality. At the onset, as well as monitoring water quality, there was supposed to be a number of other platforms, including platforms dedicated to monitoring for marine mammals and passive acoustic monitoring. So we decided to put everything together. So that was already slightly disruptive compared to what you currently see. It was to reduce the amount of assets in a very busy area with a lot of commercial shipping. I mean, we are an island, so everything has to come by port, and there are only 3 of those main ports in the country, and this is the biggest one. So we've been sending this data back on an ongoing basis for the last 4 years. Just sorry, coming back to this. So we experience waves of H max of just under 8 meters here in Dublin Bay. So even though we're very close to the coast, we do have a fairly hazardous climate. That led us to contacting ESA to look at validating satellite data in the coastal zone. And the guys in ESA and Esrin funded a 3-year project looking at coastal validation. So rather than going to pristine, picture perfect Caribbean, Pacific, Indian Ocean waters, we did it in Dublin Bay in grey, murky waters, because that's where our commercial activity is, and that's where we want to use the satellites. And so it was important to see how does it really respond in real life. Because we already had the infrastructure in place, we adapted one of the buoys we were using for Dublin Port. And so whilst we were delivering the contract to Dublin Port, we were also carrying out the validation work on Sentinel 3 and Sentinel 2. As you can see, that is the validation buoy in the image. It's very close to land. So really we were putting, sorry about that, just got a Zoom message or something. So we put this in environments that satellite data doesn't get used to, I guess, validating. People would prefer to validate in water that has lots of distance between various pixels. Just to give you an example, this is data. So for Sentinel 3 here, we had 3 overpasses within 90 minutes, which is quite rare in Ireland. The middle picture shows exactly where the Coast Val buoy is. So it's our 4th little buoy. And so the graph on the right shows how well it matched. This is really important because the guys in ESA thought this could possibly not be quite correct and we might have been making up the numbers. So they funded the 3rd year just to make sure that we could replicate this, and we could. And I guess at the end of this project, we said, well, it's all very good having these fairly big buoys, but realistically, we need to be able to do this in a way that's accessible, which led to COASTEO. As part of, and I call this slide research to commercial, because we did that in one step at the same time as it happened. So here we were able to compare satellite data with our in situ data from our data buoys. The in situ data was a tiny bit deeper, the surface measurement than the satellite data, but the comparison is really good. This gave our client, Dublin Port, a huge amount of confidence that satellite data could be used, either in a monthly aggregated product or in a daily product. We have these cloud issues, as I mentioned. So we have now set up the processing chains to do all of this. I just have a couple of slides left and then I'm done. So back to Dublin Bay, what are we working on now? Well, this slide just shows you a nice image from a wastewater treatment plant, the largest one we have in Dublin, which you can see above there from Sentinel data. And we have Landslide data as well to look at the thermal plumes. So Dublin Bay being a UNESCO biosphere, being a European capital city, there are lots of actors and stakeholders using the bay, and it's work that needs to be taken to the next level. So we are looking at measuring E. coli using satellites. So taking what we have been doing in COASTEO, linking that in with machine learning and AI to come up with mechanisms that we can use to detect E. coli and COVID by association. And so it's just the next step, taking what we have now, bringing in the machine learning and seeing, you know, what can we see with this data, what is useful, because all of a sudden, if you look at E. coli, there's a public health dimension and it becomes much more critical and much more important right here, right now. I have one last slide, Amanda. Last area of innovation that we have an interest in is ports. As I say, we have good relationships with a number of the ports here in Ireland. and we've been having conversations with ports in Portugal, so about digital twins, and again, using systems like Buoy, making it much more accessible to have ongoing monitoring, ongoing products, mixing the spatial and the temporal. So with that, thank you very much for your attention. We'd love to have conversations with people on your side of the pond and see, you know, what potential collaborations there could be in terms of marine data, machine learning for marine, as well as Earth observation. Thank you.
That's great, thank you, Charlotte. Okay, the penultimate example that we have is from Open Cosmos, and we're going back into space now. And so I'd like to introduce Florian.
Thank you, Amanda. Checking, can you hear me and can you see my screen?
Yes, we can hear and see you.
Perfect. I'll start. So thank you, everyone. So I will present you about Open Cosmos and how we are innovating using small satellites for Earth observation mission. So first, a bit about the company. So we are a space mission provider, and specifically we build satellites and we operate them. We were founded in 2015. We now have 43 employees across 3 countries. We have so far launched 3 satellites and we have 8 more in the making. So I will try through this presentation to show at least one example per slide, so to illustrate how we have been using innovation to tackle the different challenges that we have faced. So when I say that we are a space mission provider, it means that we're trying to address a one-stop shop to start from a mission idea and to go down to data analytics. And the way we do so is by addressing the different phases of the project lifecycle, from the definition and maturation to building the satellite, launching it, and operating it. Of course, we don't do this alone. We do this together with partners and customers, payload providers, rocket providers. The specificity is that we build the satellite ourselves and other parts are done by partners. And that's one of the main, let's say, innovation point, is that we try to provide the space mission provider as a one-stop shop. Of course, the challenge of this is the multiplicity of interfaces, and that's where we had to innovate, is find what's the best way to be both scalable, but at the same time being able to interface with multiple partners. Due to this fact, we actually have a number of satellite missions at different level of maturities. The first one you see at the bottom, and the very small one, was a 2 CubeSat mission that would launch in 2017, deployed from the ISS, and that re-entered the atmosphere safely in 2018, so nearly 1 year after. It was for a scientific measurement of oxygen within the atmosphere. Last month, we launched 2 other satellites, this time for Internet of Things, so 2 3U satellites. They have performed successfully LEOP and in-orbit commissioning, and they are now operating as routine operation. We have other satellites, as mentioned in the meeting, another one which is a 6U Earth observation satellite with a Spanish partner. And now I'm going to present you 3 other missions, which are the one I'm going to dig into in the next slides. So the first one is what we call the Mantis mission, which is part of the InCubed program, which is a 12U Earth observation mission. Another example is Fisa2, so the successor of Fisa1, which is part of the PhilLab initiative. And finally, NanoMaxSat, which is a scientific mission for Earth magnetic field. So as you can see, I go in reverse order in terms of maturity. So you can also see the innovations we have addressed, the one we are currently addressing, and the one we will address in the future. So I start first with the Mantis project overview. So as mentioned, it's part of InCubed, and it is funded through Esa with funding from the UK Space Agency. And it is focusing on addressing the mission idea is originally to help address 3 main factors in the oil and gas and mining sector, which is to have better market intelligence, knowing what is being done, to have better knowledge in terms of regulatory compliance. So in order to have a better self-reporting on environmental impact, And finally, we need to have a better monitoring of the long-term project, which go through different life cycles, which can last up to 10 to 20 years, and which require a lot of planning and understanding. And we try to address this problem using small satellites, CubeSat, which are, let's say, form factor is typically a microwave, and that is typically between 10 and 20 kilograms. So as mentioned, the way we do it is that we don't do it alone, but we act as an integrator. You can see here, so the satellite in itself, which combines a payload from our partner Satlantis, and the data is afterwards processed by our partner on the ground Terabotics. So as you can see, and as mentioned before, part of the specificity of the InCubed program is to have innovation, in that case in the payload and the concept, but after also traction from market in terms of what is the actual need of the mission. So the overall mission proposed is a 12U 16 kilogram remote sensing satellite for a resolution down to 2.5 meters after post-processing. The area covered per day would be around 31,000 square kilometers, and the target is to deliver data within 4 hours of acquisition. So the three main innovations that I can mention. First one is the use of a binocular payload and super resolution. One of the main challenges of small satellites, and specifically CubeSat, is both within the volume and the power. Specifically, when you want to have a high resolution imagery, you need to have a big lens, and effectively when you're using CubeSat, you are limited. So one way to go around it is to use this binocular payload and super resolution, which allows you to achieve a better resolution that you would with the equivalent size of the lens. The second part, and as mentioned before, is regarding the interfacing, is that we need to ensure the payloads that we have chosen can be accommodated within the satellite platforms that we are developing. The way we do so is by providing what we call an open kit. This is a platform emulator, which emulates the structural part, electronic part, and power part of the platform early in the project, meaning that the payload provider does not have to wait a long time before checking if all the interfaces match. We provide them this emulator so they can do a co-development and reduce the risk of the interface as much as possible. And the final point worth mentioning is the onboard cloud detection algorithms that we want to do. The challenge associated is that due to power restriction, we have also a restriction in terms of the amount of data that has to be downloaded. It was mentioned it's even more important in terms of hyperspectral. In our case, we're using multispectral, but we still have the need to optimize what data we bring down. And that was what introduced the need for having onboard cloud detection so that we download only the images which have a minimum cloud cover. I am now moving to another project, which is not part of InCubed, but still part of an initiative of the PhilLab, and which is Fisa2. So this mission is innovative because its purpose in itself is to act as a flying laboratory for onboard artificial intelligence application. So once again, as we said, that's something we do in partnership with other entities specialized either in the payload or the development of application or specific hardware that we have to host to accommodate the AI application. And specifically in that case, we want to test a number of different applications, for example, transforming an image into a street map to have anomaly detection or forest monitoring, as well as vessel monitoring. And the key point here is really to be able to test a number of applications, but also to upload new applications that could be tested further down the line. Really, the point is to have this flying laboratory. The final mission, and perhaps the most complex of all, is what we call NanoMagSat. This is a mission to monitor the Earth magnetic field and ionospheric environment. It's done, as mentioned, so with IPGP, with the Institute of Physics in Paris, together with CELAT, with an electronic provider, and University of Oslo. So the big challenge of this mission is its complexity through different aspects. The requirements here are effectively driven by the coverage we want to have in terms of local time, spatial resolution, and geographical coverage. For people who are familiar with Earth magnetic mission, this could be potentially a successor of SWARM, and the difficulty is that SWARM is a far bigger spacecraft, I think 300 to 500 kilograms. What we're trying to provide is a system with a better coverage, and that's through using small satellites. So the innovation we had to bring forward was first a number of orbits different that could first provide the required coverage and be also complementary to a potential swarm-bees that could still be in operation. The satellite in itself would be a 16 CubeSat, and there's the main point and challenge we have to face is the magnetic noise created by the satellite, because as we want to monitor the Earth magnetic field, we need to have the sensors as far away from the body of the satellite. So overall, what we have is a 16 satellite with a deployable boom of a couple of meters, which will host a miniaturized absolute magnetometer at the tip of the boom, co-located with star trackers to obtain a very high orientation accuracy. This is complemented with a high frequency magnetometer in the middle. And we have finally dual frequency GNSS and multi-needle long near probe to complete the suite to monitor the ionospheric environment. So the main challenge for this one is effectively to try to have the right tipping point between keeping what has worked before while still proposing something new to enhance the capability. And the point of this mission is to provide a starting point for local, scalable, and collaborative constellation solutions that could accept even further initiative from other countries, not necessarily within Europe, and is really stretching the point of innovation, which is we always need to try to keep what works, but try to improve what can be done. Which I think was very well synthesized in one of the first presentation from the Fila, which is to say that you have to be a little bit crazy, but not stupid. So with this thought, I conclude my presentation. I welcome any question. Thank you very much.
That's great. Thank you, Florian. And then I'd like to introduce Patrick, who is an example, comes from an activity of InCubed, which is now back down to Earth in the downstream value chain. Thanks, Patrick.
Good afternoon, good morning, everyone. My name is Patrick Stoppelman, live here from Amsterdam, the Netherlands. I'm going to share my screen. Hope this works. Share. Should work, yes. Go to present.
Yeah, it looks good.
Great. So I'm here, I'm from the company SkyGeo, and I'm talking today about the Sat4Flot project. It's an part of the Esa InCubed program. And here on the front page, you see already quite some disturbing images. This is really taking place. In this case, it was in the UK. And I'd like to come back to the situation. So first of all, SkyGeo, who are we? So SkyGeo is what you typically call a space downstream company. So we are 12 years now in business, and we have 35 staff, a very international team. You can see on the globe on the right side where we are in Europe, in South Africa, and in Canada and the US. So we do interferometric synthetic aperture radar. INSAR is the abbreviation. So we have a bunch of INSAR specialists, PhDs, and other masters. We have consultants. And what is relevant to share with you is that we have a geodetic DNA and approach, and that distinguishes us from companies that see it as big data. So we try to really master what we do and to bring it back to the situation in which it takes place, the so-called geodetic DNA of ours. We have a platform called maps.skygeo, and also very important, we have a SkyGeo Academy, which is a subsidiary and offering many courses, training, and helping both companies that want to work with INSAR for the first time, and also companies that purchased INSAR data and want to expand. So our clients, typically civil, all kinds of civil constructions, mining, energy, government, and as said before, global activities in America, strong presence, Africa, Europe, we do a lot in Europe, Northern Europe in particular, Australia, New Zealand, and just a few names, Shell, OceanaGold, State of Oregon, well, there's a whole bunch of it. A few examples of what we do. So here, typically, you see large-scale ground movement, and it is causing post-mining damage. And this is what's taking place in many areas of the world, also here in Europe, where mining is being abandoned and the groundwater pumps are being stopped. And over a period of 10, 20 years, you get all kinds of effects. And here you see a situation where there is large-scale uplift, but if you would zoom in, you would see that there's big differences. There's like potential sinkholes. And these red lines are breaches in the underground, and they cause also strong differences in pressure. Another thing we did here, you see beautiful Amsterdam. It's in a UNESCO city, goes back to the 16th, 17th century. And so many of these monuments have wooden pole foundations, and these wooden poles suffer from all kinds of bacteria, groundwater fluctuation, warming up of the earth. So we developed here for an entity that owns 100,000 apartments, a risk indicator for them to find out what's the status of these buildings, if we have to change these buildings for modern standards, so get them more energy efficient and upgrade them to standards of current living. Another example is infrastructure. Here you see rail tracks that are next to a highway. And here is an example of severe deformation of the tracks. And we're studying this together with the operator. Another example is landslide monitoring. This is where we do C-band Sentinel-1 data. And it's laid over the LiDAR view that we got from this particular client. And I cannot share everything, but here you see that there's clear movement in the road that is going from south to north. Another example is sinkhole detection. This is what we do on interferogram analysis. And here is an example of where we see a precursor appearing and where we inform the client and make them aware of potential movements. And last but not least, monitoring of mining locations. Here is an example of Sentinel-1 C-band and of TerraStar X. It's a very high resolution product that we purchase commercially. I think this is the moment to step over to the SAT for Flood, the project, and it reads here dam failures. And this is what I like to tell a little more about. So, having our roots in the Netherlands, meanwhile being very international, living below sea level, and the risk of dam failure is among us. And so the consequence of dam failure, it's taking place in many countries, many spots, is huge. And so there's a worldwide need to improve risk management related to dam failure. It's something we identified also in collaborating with research institutes. And so here on the right, you see some examples of how a dam can fail. There's quite a lot of study material available. And so we looked deeper into risk factors and into versus observable features and observable by using remote sensing data. And we decided to concentrate on the two red blocks on deformation and soil moisture, and all the others are partly attached to it or will come in a later phase. And this led us to, we make use of the Copernicus network, so Sentinel-1 for deformation, Sentinel-2 for soil moisture. And this made us to develop the SAT for Flood service. And let me first tell you what it is. It is a service detecting weakened water defense structures and reservoir dams. It's based on two integrated Sentinel services, but it can also be commercial high-res data. And so Sentinel-1 for radar, for INSAR, as I explained, and Sentinel-2 for soil moisture. And so the service that we developed has an aim for a typical asset managers, infrastructure owners, relief organizations for crisis management, institutions like World Bank, insurance companies, real estate, mining companies, and international engineering advisory companies. So quite a big variety. Our project is something what you can call a downstream development challenge. So what we had to develop is to integrate Sentinel-1 and Sentinel-2 S1 and S2 data, and they have very different characteristics and dynamics. And we had to investigate risks, what can be observed with the combined data set. So there is a strong interdependency between soil moisture and deformation. And so we had to identify what it was and to integrate it into a, let's say, online service as part of the InCubed program and qualifications. I like to take here a little step to what it meant for us to work within the InCubed framework. It goes back to Amanda Regan, her first presentation. So how to organize yourself. So what we did is we were working under the potential umbrella of a funding of maximum 50%. So the other 50% of this investment we had to fund by ourselves. And so in our case, we formed a consortium with 2 other partners that have other expertise, and we've identified business partners that were willing to look closer to and to reflect on what we do and to offer research locations. There were some preliminary Esa qualifications. So as you can see here, we made a business plan for the commercial aspects, and we made, for example, a system and service architecture plan. We came up with commercial objectives, a whole bunch of them, on what we're going to deliver.
Patrick, we're not seeing your slides advancing. I wonder.
That's weird.
Yeah, we're sort of stuck on the to be developed slide. I wonder if you stop sharing and start again. Sorry.
I will stop sharing and just see. Are you able to see me?
Yes.
Yes. So let me go back. Were you interrupting me as soon as you discovered that it?
We didn't go too far
Okay.
We saw most of your slides. Yes.
Let me go back. Let me just go back and see if the technology.
So Patrick, go back to the slide where you're talking about different players in Stratford. We didn't see that slide. That was the first slide.
Okay. Are you seeing my? No, I can see on my iPhone. It's still working. The wheel is still turning.
It's it looks like it's starting to show.
Yeah. It's not really progressing.
Maybe try one more time, Patrick,
Yeah.
and try turning off your camera too. I don't know if
that's a good point. I will do that immediately. Yes. Just 1 second. Apologies, I will try to share again.
It looks like it's still struggling.
This is when you do live.
Right.
This is when you do.
Let's see. I can share what I have, but I don't have all the
I gave you sort of a first draft, and you should be able to get it back up here.
Yes. Let me.
So I will stop sharing for now, and I will go to what I sent you.
Let's see. How does that look? Does that look roughly where we were?
Yeah. Let me only go back to so that I know what I'm going to. What I just give me a second. Again. Yeah. Okay. So the challenge, I think I left more or less here the presentation. So the challenge was to integrate these 2 sensors. And as part of that, yeah, we should go then ahead to, please go forward. Yeah. Yeah, go forward. One more. Yes, so here we are. Yes, so what I try to explain is working within to how to organize yourself. So here what we did is we organized, so we were working under a program where we got 50% funding. We needed to invest 50% ourselves. And so we organized a consortium and we found business partners. And this is how we presented ourselves. And on the next sheet, yes, I want to demonstrate how we work. We produced a business plan for the commercial aspects, and we delivered, for example, a systems and service architecture document, a lot more. And this was all presented as a preliminary element for the process. And on the next slide, you can see that we developed, or we defined also commercial objectives on how this service would look. On the next sheet, you can see we came up with the project plan. And on the next sheet, you can see how we, with our partners, identified locations where we could apply the service. And I think this is a good moment to go over to the more technical part. So let's go on to the next sheet, please. Yes, and the next one. So this goes back to where I left. So we have the risk factors and the observable features, so the deformation and the soil moisture. And on the next sheet, I like to tell a little more on the technology as far as people are not familiar with it. So INSAR is like GPS from space and no hardware needed. And here you see an interferometric synthetic aperture radar example. This is of a levee where there is severe deformation going on. And on the next slide, please. I want to explain a little bit on how it works. So we do this in 2 or 3 steps, otherwise it takes too much time. So radar, what we use is consisting of both amplitude and phase. And so we cut off the amplitude and we use the phase, and then we have every 6 days a new image. And we start taking, we subtract phase B of phase A, and this is how we get these interferograms. And of course, we do all kinds of corrections, all very technical. And this is how we get into, if we go to the next slide, please, to something which we call then a full wave cycle estimation. We do the phase unwrapping. This is where is our specialization. So there's a lot of assumptions, and most of all, we need, the more we know about the situation on the ground, what's going on, we are better able to do this. On the next slide, you can see there's all kinds of phase unwrapping models that we developed and applied. And so new for the SAT for flood is also that we developed a soil moisture model that we apply. What you can see here also is that, for example, the last one, the breakpoint, is something that we typically apply where we do forensic research. There's some kind of incident taking place on a specific date. It has to do with the intervention, and there we can go back. If we go to the next slide, this all results into a deformation time series, like showed before. And so here we have a linear deformation rate as an average of 32 millimeters a year. It's quite severe. I can tell a lot. On the next slide, something on the explanation of soil moisture. This is where our partner is specializing in. And if we go to the next slide, this is Sentinel-2. And here there's every 5 days an image. And this is already interesting to see, because here you see clear distinction between radar and between optical, because if optical is being disturbed by clouds and radar is typically not disturbed by clouds. So this is already a difference in technology that we needed to combine. And I hope those sheets will be in here. Yeah, what I propose as an alternative is that we go, so there's missing here a bunch of slides, to an example that we studied. So we go to the next slide. And one more, yes. So this is known failures. This is a database that we looked into for application. And so I skip, because the slides are not here, I skip part of how we developed it, and I go straight into a real situation that took place last year. It's in the US, the Edenville Dam. It's a grass-covered earth-filled dam These are all details that we take into consideration. And heavy rainfall, seepage, etc. So let's first go to the next slide. Yeah, this doesn't look very well. This is where the dam collapsed. And here, if you go to the next slide, it was my intention, let me see if it's still possible, to show a little clip from YouTube. So if you allow me for 1 minute to see, yes, let me try and share again. Yes, and now see if this works.
There it goes. There it goes. There we go. There's the rush.
Yeah, I want to leave it here.
Patrick, you've got 1 minute.
Yeah, that's fine. I want to go to a few final sheets. So here, I'm going to show you. So what we discovered is that there was seepage, where you can see the red circle seepage behind the dam going on. And then in September 19, you can see here on the red dots, there was something going on, part of the dam near saturation. This is all looking backward. And then we discovered that there were most likely works taking place at that location, some kind of in situ work in the dam. And then we see even more saturation coming up. And then suddenly in August, so we moved from, we see a swelling. This is also very interesting in the insular. And then this is after the fact. And so it's going quite fast, but this is some screenshots of how we would have been able to detect the situation of this Eden Dam with $175 million lost. This concludes my presentation. Apologies for the technical issues.
Thank you very much, Patrick.
Yeah, I want to say thank you to. I want to say thank you to all of you. That was we've really packed a lot into the last 84 minutes or so. There was a lot of amazing work, so much to still unpack in terms of details that we weren't able to get to. But I'm really grateful to the 5 of you for showing up and presenting, and I'm really excited to be able to share this presentation with the broader community. And the chat box has been pretty busy. I see that some questions have already been answered there, but I'm going to try to bring just a couple to the fore with the remaining 4 or 5 minutes that we have here. The first one I want to highlight, it's actually for Charlotte. It's from Dave Jones. Charlotte, can you speak to whether you've done any work with identifying harmful algal blooms?
Yeah, so I didn't say anything about harmful algal blooms because they've been worked on by a lot of different groups, and we're focusing on, I guess, some of the issues that haven't had a huge amount of focus, and issues which are slightly different, a bit more complicated, such as seaweeds or jellyfish or E. Coli's. But yes, harmful algal blooms are one of the products, the services we are looking at on the COASTEO project with the mini buoy system, because we have a chlorophyll sensor on board.
Thank you so much, Charlotte, and thanks, Dave, for that question. Looks like we have a question from Thomas. This one is for Patrick. Is there a limitation to the size of sinkhole you are able to identify, given tree canopy is not too dense?
Yeah. I guess that is then the size, the smaller it gets. what we always say is we would have to better understand the local situation. It depends on what imagery is available. It depends on how fast or how slow it's developing. So I cannot just answer it up front. Overall, we're open for any kind of technical discussion because this is all the time what we need to do before we can find out if it is feasible. But on average, I would say that we are progressing and we have various sensors that we can apply.
Thank you. Looks like we have another comment from Dave Jones about a lot of these topics being very much of interest to the ESIP community and wanting to create an ecosystem of innovation and learn from you all, possibly partner in doing that. Thank you, Dave, for those thoughts. Does anyone else have another question? You're welcome. This is a small enough group. You're welcome to unmute and speak up.
I will say, Megan, from Dave's question, I speak from InCubed, but also on ESA's behalf, that we're always interested in partnering because we're dealing with Earth observation. So that doesn't mean just looking at one little part of the Earth. We're dealing in Earth systems. So we're open for discussion for any potential partnerships or mutually workable solutions. So I'm very happy to be contacted and for him and his team to get in touch with us.
Wonderful. Well, it sounds like there's still so much left to unpack, as I mentioned, but I think some connections were made here today, and I think we'll make some more connections by sharing this more broadly. I did want to share just one sort of closing slide to send us off. And again, I just wanted to thank everyone for participating. I want to thank our 5 speakers for all the work you put into sharing what you do. And I wanted to say thank you for our participants and your very fine questions. This concludes our jam-packed webinar for today, but we will be back in May in just a few weeks with another webinar that we'll announce shortly on our website. Just a reminder to all to stay up to date with all things ESIP, including the announcement of the next webinar and any updates on the summer meeting that I mentioned. You can subscribe to our Monday update mailing list, which is listed here in the bottom left-hand corner. And I also want to remind everyone that this webinar was recorded and we'll have it up on YouTube shortly. So please feel free to share as widely as you like.